Hello, a big welcome again for the next chapter we are taking. Here it is Principle of Mathematical Induction. Students, let me try to tell you that this is one of the very important part of maths, because this PMI, which we call in short PMI, full form is Principle of Mathematical Induction, is a very strong tool for proving many important theorems, right, where particularly it is related to the positive integers, that means natural numbers. So just to start with, I'll take an example and then I'll go for the statement of the principle of mathematical induction, and then we'll take problems. Basically, if we see, this is a very small chapter, it will not take much time, right? So we'll go on little faster move. Let's start with. So what does PMI motivates us, right? So let's take an example. Just try to remember, you all have seen something called dominoes, right? This is a very important interesting game or maybe an activity which is being observed in China basically, or Japan. So what they do in case of dominoes, those small plates, colorful plates, they arrange in a certain gap, right? And then you have to hit the first one. Once you hit the first one, what happens? It hits the next and then next, and all this sequence gets fall, and then ultimately a very nice design comes up, right? So you have seen. Now what is the trick behind this, right? Forget about the structure they form, that is the activity of the artist, but I'm talking about falling the plates. What is the maths behind it? When the first plate you hit, right, then you have to keep the second plate in such a way that when this falls, it should hit the other plate in such a way that it starts falling, and then this should hit the next. What does it mean? That means this is a sequence to continue. The first, if it hits the second, then second should hit the third should hit the fourth. Now just think one thing. Supposing that in between somebody remove one of the plates, right? What will happen? Can you tell? Suppose these are the two consecutive plates and someone has removed this. So other plate will be coming here. So till the plate here, it will fall like this. But as there is a gap here, once it falls, it will not hit this. That means this sequence will be broken. So once this sequence will be broken, your whole dominoes, that will not fall and the structure will not be constructed, right? So that is the fact behind, or the process behind our PMI, or principle of mathematical induction. So how we will prove? Let us just see. First, let us take the statement. I will not explain you in very big detail because there is a background actually. That background is little bigger. So let me directly start with the statement. Right, before I start with PMI statement, let me give the statement of the word statement, right? In case of maths, what do you know by statement? What do you mean by a statement? Very important to know. It is a meaningful sentence, right? A meaningful sentence or argument which is either true or false, but not both. Not both means, by the word not both, I want to mean that it should not be ambiguous, meaning that you should not be able to you should not have a confusion that okay, this is true, no, for that it is true, for this it is wrong. It should not be like this, right? So for some time it is true, for some time it is wrong. It should not be like that. It should have a concrete value, true or false. You should be able to say this is true. Okay, this is 2 plus 2 equal to 4. What you will say? True. True means true. There is no question that it is wrong. So that is a statement. What statement? It's a mathematically accepted statement. 2 plus 5, I am saying 10. Yes, it is false. So this is also a mathematical statement, right? So we have the definition of statement. Now we are going to talk about the proof of such arguments where integers are involved, positive integers, with the help of PMI. Let's start with the definition of statements of PMI. There are various statements. I am considering the simplest one, which will be using for the proof of the statements. It is PMI, that is principle of mathematical induction. Let Pn be any argument or statement if number one, Pn is true for n equal to 1, means when you put n equal to 1, that statement should be true. Pn is true for n equal to k plus 1 whenever it is true for n equal to k being a positive integer. Then Pn is true for all n belonging to natural number or all n which is positive integer. Now here this is the main part, the body of the PMI. So here what we'll do, this particular supposition step, when we say that the result is true for n equal to k, then we have to prove further that the result is true for n equal to k plus 1, right? So when we suppose that it is true for n equal to k, then we say that step as a hypothesis step, right? So let's start with the problem. This is all about, you have to learn the statement first, because you have to regenerate the statement at the end of the problem, each and every problem. That's the demand of the problem, right? Okay. So to start with, I'll be using a very common question which all of you know, that is the sum of the first n natural number is n into n plus 1 by 2, n into n whole into n plus 1 by 2, right? So I'll write in the form of question. Question number 1 say, prove that 1 plus 2 plus 3 dot 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 n is equal to n into n plus 1 by 2 where n belongs to natural number, right? Where n belongs to natural number. I am not saying by PMI, but I can write, no problem. Let me write, prove that by PMI, right? So I am going to follow the steps. Be very alert to observe the steps. It's very easy in fact, right? So proof. Remember those steps. First step, you have to name the argument, right? So we'll write, the given statement is, Pn. This is the style how we denote a statement. This is 2 dots. There should be 3 dots only. Do not write more number of dots. This doesn't carry any impression, right? This is the given statement. Let me again try to tell you, you should not put more than 3 dots. It is not required at all. Putting more dots doesn't mean that you are more correct. 3 dots, each dot have meaning. First dot n, second dot so, and then on, and so on. Finished, right? So 3 dots are enough for you to express what you want to express completely with the help of this gap, right? Okay. Now we'll start the first step of the induction. What is that first step? The first step is that it should be true for n equal to 1. So let's prove it. for n equal to 1. For n equal to 1. See, I am trying to take the easiest one. I will prove by left hand side equal to right hand side. There are other options also which I am not going to take up. For some problem we will be taking. Okay, n equal to 1. N equal to 1. Always I give you a trick. Whenever you prove it for n equal to 1, from the left side take only one term. That's all. Only one term. So this one, first one. So LHS is equal to 1. RHS, you put n equal to 1 here. So what you will get? This will be giving you 1. Ultimately what you arrive at? LHS equal to RHS. That means these statements will be proved or is true for n equal to 1. So I can write like this. Therefore, Pn is true for n equal to 1. Now see, this is one of the very important step. It's over. Now till here you will be getting a mark, 1 mark. If I talk about marks. Now we'll go for the hypothesis. That means we'll now go for the supposition step. What is the supposition step? Let the result be true for n equal to k, where k is some positive integer or natural number, you can say. Okay, fine. That is what I can write. If it is true, pk in place of n will be getting k. So you modify the statement. Okay, this has to be marked. Now remember, this is one of the very important part. This has to be used in the proof of the result for k plus 1. Right? So it is very important to note. Right? Now I am going to prove the result for n equal to k plus 1. So you write that particular objective also. Now to show that Pn is true for n equal to k plus 1. So this is our objective we have noted down. Now let's move on to the main part. This is the main part, which is the induction part. Very important part, right? So let's start with the proof. That means now we are going to prove the whole result for n equal to k plus 1. So this time what I have to do, I have to take n equal to k plus 1 and I have to see the left side of the statement, right? So for n equal to k plus 1, what is the left side? Just you see, if you have considered k, your whole expression will run up to k. But now you are considering up to k plus 1. So one more additional term will be there. That is what? K plus 1. But remember, till k you have to write. Why you will come to know just after 2 minutes. So this is k plus 1. Am I clear to you? For proving k plus 1, you have to write one additional term to the hypothesis. Here you have done it for k. So one more term you have to add or multiply it, whatever is the expression's demand, right? Now why I am saying to write this k? Because now you see this particular part can be easily replaced from this particular expression. See that? So that star gives you this as k into k plus 1, k whole into k plus 1 divided by 2, and this is k plus 1, this one. Now, right, you can take LCM, but do not take LCM if there is a scope to take common first, right? To take the common one out, then your calculation will be easier. So here I can take k plus 1, so I will be left out with k by 2, and here it is 1, and now work it on. What you will get, right? What you will get? You will be getting this as k plus 1, and then this is k plus 2 divided by 2. As a whole, if you try to simplify, this is the result. So you have come up to the conclusion, and this is k plus 1 into k plus 2 divided by 2. Now you have to again see whether you are going to get the same thing once you replace n equal to k plus 1 in the right hand side of the expression. If you get, you are done, right? So now you see, we are going to replace n equal to k plus 1 in the right hand side. Also, for n equal to k plus 1 RH size, n, it is the place for n, then n plus 1 was there, so it is k plus 1 plus 1 divided by 2. What did you observe? Is that obtained? Yes, you got. Both the sides are equal, right? Both the sides are equal. So you can write LHS equal to RHS. So LHS equal to RHS for n equal to k plus 1. So you now give the concluding step. Now you have to go for the concluding step. This is the first problem. So I'll be writing all the steps, but other problems I'll not write all the steps. Okay. So what you'll write now here, therefore Pn is true for n equal to k plus 1. N equal to k plus 1. Now it's time to again bring those statements, right? I'll write the concluding statement in the blank space here, right? Thus, right? Thus, Pn is true for n equal to 1. Thus Pn is true for n equal to 1. Also, Pn is true for n equal to k plus 1 whenever it is true for n equal to k, right? Whenever it is true for n equal to k, where k is a positive integer or natural number. Therefore, by PMI, Pn is true for all n belongs to natural number, right? So you write like this. But at last, if it is possible for you, when you go for the deductive reasoning during the exam, your board exam, so you should write again the original statement. Therefore 1 plus 2 plus 3 up to n is equal to this, right? So that's all. So I have taken this problem. Another problem which is well known to you, that I will be taking. First slide, we'll be going for the book problems. I'll take 2-3 periods for this. So now let's take the another problem, right? So you, if needed, you pause the video for some time and then you please see it, note it, do it yourself, and then try to see whether it is understood by you or not. And for any kind of questions, you can ask me through my mail, right? Already mail will be given in the link. I'll try to upload the class notes also, but it may take a little more time. So you see the video after 1 week. Once you see first, check the class, then for class notes, maybe 1 week, right? Okay. So question number 2. This time I'll not write anything about detail, just the expressions. Say you would like to prove this. 1 plus 3 plus 3 square, like this, 3 to the power n. 3 to the power n minus 1, let me make. This is a GP, geometric progression. Those who studied some other maths, extra maths, they might have got it, but in CBSE syllabus it was not there at class 10, right? So GP tells you this as, this will be 2, right? Then these things. So you have to prove this result. So now Let's start with the proof. Right? Okay. Proof. So here see, as I told you, I will not write in detail the statements this time because the same statement will be recurring. So I do not want to write the same statement. This is a statement which you have to prove for n belongs to n, capital N. First, we have to prove the result for n equal to 1. So directly I'll write for n equal to 1, LHS is 1. I write RHS here. You put, if you put 1 for n, you'll be getting this as 2 by 1. That means LHS equal to RHS. Therefore, Pn is true for n equal to 1. So one thing you did. Now we have to go for the supposition step, right? Supposition step. So let the result be true for n equal to k, right? K belongs to some integer. Therefore, what you will be getting? Pk. So Pk will be 1 plus 3 square. Once it is n, you run up to n minus 1. So k means you will run up to k minus 1. So your answer is 3 to the power k minus 1 divided by 2. Fine. This has to be used. So you write, now you specify your objective. To show that Pn is true for n equal to k plus 1. So this is your objective. Now we have to prove that if n equal to k plus 1, this statement is again true, right? So let's move on to this. It's a very easy problem, right? We have done it for n equal to 1. For n equal to k plus 1, what is LHS? Again I am saying, reminding you, when you write once this particular one, then add one extra term. That extra term will be containing power what? 3 to the power k, because you can easily identify powers are increased by 1, right? Now from here to here, you can use this supposition step. That gives you 3 to the power k minus 1 divided by 2. Then this is 3 to the power k. Here nothing is common, so do not think about common. Just you think about taking LCM. So if you take the LCM, what you will be getting? These things, right? Just see how to manipulate this. Many of the students commit a mistake over here. That is, this is 2 into 3 to the power k. They write 6 to the power k. But remember, this is 2 multiplied 2 3 to the power k. 3 to the power k is itself one different entity. So now how will you work out? Very simple. Here 1 3 to the power k, and here there are 2 3 to the power k. So total how many 3 to the power k? 3. So 3 3 to the power k. This is not decimal point, this is into minus 1. The next step will be 3 to the power k plus 1 minus 1 divided by 2. So this is the result we get. Now right hand side also you put n equal to k plus 1. In the right hand side also you put n equal to k plus 1 and check whether you are getting correct or not. Right? If it is correct, then you are done. So for n equal to k plus 1, what is RHS? 3 to the power k minus 1, it was n minus 1, right? In place of n I am putting k plus 1. So now clearly what did you observe? LHS equal to RHS. Therefore Pn is true for n equal to k plus 1, right? Now the concluding part I will not write, because after this you have to write again those statements what I wrote here in the first problem. Same thing, simply copy it down and just attached, right? So this problem I leave it here. One more problem I'll be doing first, and then I'll go for the next period, right? One more problem. This time also I'll be taking a GP, but this time GP in general form, right? Let's see. Okay. If you think that I am moving little faster, pause the video, read it, reread it, generate it, right? You'll be understanding this. Question number 3. Question number 3. What I have to prove is this: a plus ar squared, then ar to the power n minus 1. This is equal to a whole into r to the power n minus 1 r minus 1. Okay, r greater than 1 I'll fix, right? So this is what you have to prove, right? So let us start with this. Again same thing. So here Pn, what will be Pn? This is the statement, right? This is the statement. This is the statement. We have to prove it for n equal to all natural number, n belongs to all natural number. So first, as per the rule says, or PMI says, we have to prove it for n equal to 1. So for n equal to 1, LHS, the first term, RHS, put n equal to 1 here. So r to the power 1 minus this, r minus 1, they will get cancelled, so a will be there. Therefore, what you will get? LHS equal to RHS. Therefore, Pn is true for n equal to 1. Therefore, Pn is true for n equal to 1. You are done with the first step. Now supposition step, right? Let Pn be true for n equal to k, where n is a natural number. Therefore, I'll be getting this as pk. Then this will be ar square. Where up to it will run? It is k minus 1. And your results will be a whole into r to the power k minus 1 divided by r minus 1. This has to be used further, so star we have marked. What is the objective? To show that Pn is true for n equal to k plus 1, right? Till now you may not get more taste here because we are not taking challenging problems or like different problems. This is just to start with, so we'll be taking different problems also. Let's just tackle this problem, right? In the next period you'll be getting definitely some problems which will definitely like make you feel that you are doing something bigger, right? Okay, so now we are going to prove this result for n equal to k plus 1. So now let's put for n equal to k plus 1, let me put LHS. LHS, what is LHS giving you? A plus ar square. You go on like this, k minus 1 will definitely come, then it is k, right? You can easily identify that we have to add one more term to this expression, right? So now from here to here, how will you prove? This is the result. This is a, then r to the power k plus, r to the power k minus 1 divided by r minus 1, and then a r to the power k. Now as you did earlier, you do just simplify, nothing more you have to do. You have to just simplify this. You just simplify. If you simplify taking LCM, what will I get? A r to the power k minus a, then this I multiply, it is a r to the power k plus 1 and then this is a r to the power k minus. Now this and this term will get cut, two terms will get cancelled. So what you will get here as r minus 1, and here a r to the power k plus 1 and minus a. Now you take the a common, right? There will be no change in the denominator because denominator is not dependent on the value n, right? So here we will be taking a, so it is r to the power k plus 1 minus 1 r minus 1. So this is the outcome ultimately when we put n equal to k plus 1 in the left hand side. Right, now we have to put n equal to k plus 1 in the right hand side. Right, also for n equal to k plus 1, what is RHS becoming? A r power n, n should be replaced by this O. This is directly obtained, right? So what you can write, therefore LHS is equal to RHS, that is Pn is true for n equal to k plus 1. And then again, once you come up to this step, please write that particular statement what I have written here in the corner, right? So that is for your concluding step. So now today this is the first period, so I give you time, maybe 1 or 2 days you will be getting. So after that we will come to the next lecture of this. Okay, till then, bye.